Welcome back everyone. In this lecture, I will actually tell you how to compute the spectrum of Cayley graphs. So, let us actually define some terminologies which are used in the study of spectrum of Cayley graphs. So, let us fix this group cyclic group of order n. So, let us take G, which is Z modulo n Z, and if we actually take a Cayley graph of this Z modulo n Z, and we call that as circulant graph. Okay. So, any, because Cayley graph indeed depending upon the generating set. So, for any generating set, you call Cayley graph of this Z modulo n Z to be circulant graph. So, any Cayley graph of Z modulo n Z is called a circulant graph. Okay, so let us justify this definition. So, what is circulant matrix? I believe some of you must have seen that. So, let me define this circulant matrix, and then we will connect this circulant matrix with the circulant graph. So, what is circulant matrix? So, an n by n matrix, it is called a circulant matrix if it is of the following form. So, if you write A equal to A naught, A 1, etc., A n minus 2, A n minus 1, and then you just take this row, and then you just use Z modulo n Z to act on that by cyclically permuting. So, then what you get is A n minus 1, A naught, and A n minus 3, A n minus 2, like this, and so on. And at the end you get A 1, A 2, etc., A n minus 1, A naught. So, this is the matrices of this form, they are called circulant matrix, and circulant matrix they have a very close relationship between with the circulant graph. Okay, let us see that. So, first to observe that we make the following observation. We see that a matrix is circulant if there exists a function f from Z modulo n Z to C satisfying the following condition. So, let us actually write it down. So, A is circulant if there exists a function, actually we can say that if and only if there exists a function from Z modulo n Z to C such that this ijth entry is given to be f of this difference between this j class j minus class I. Okay. So, let's go through and then see what is really happening. So, if we take this ai to be, if we take ai to be f of I, then this f is indeed a periodic function. So, that means it is a function from Z modulo n Z to C. If you denote ai by this f bracket I, then from here it is clear that the entry aij is exactly equal to f of bracket j minus bracket I. Okay. So, that means this is exactly equal to A bracket j minus bracket I. So, of course, we are going modulo n. So, 0 to n minus 1. So, that is the indices that we use for elements of Z modulo n Z. So, this is identified with bracket 0 etc. bracket n minus 1. So, now conversely given function f from z modulo n z to c, if we denote this aij to be f of bracket j minus bracket I, so then it is clear that aij is indeed circulant matrix. So, let us just write it down, then it will become clear actually. So, what we have done, we have denoted aij by f of bracket j minus bracket I. Then you can see that if you start filling these entries, then what you have here is f of, so this is the like 1/1th entry which is f of 0. Then this is going to be, so okay, let us write it here. This is 1 1, this is 1 2 etc. 1 n, and then here you have 2 1, 2 2 etc. 2 n and so on. So, these are all the entries. This is n 1 etc. n n. So, now all we do is we take the difference between j and I and then putting it there. So, then you can see that this is going to be exactly f of bracket 1 and f of bracket 2 and so on, f of bracket n minus 1. And similarly here it is going to be f of bracket n minus 1, because minus 1 is identified with the n minus 1, and similarly here f of n minus 2 and so on, then you get f of 0, sorry here f of 0 here, f of 0, then here you get f of n minus 2. So, here minus 2 is identified with the n minus 2 and so on. So, then it is clear that what you get is the resulting matrix is indeed a circulant matrix. So, now with this observation that A is circulant if and only if there exists this periodic function such that f aij given by f of j minus I. So, using this it is easy to see that if you start with any symmetric subset of z modulo n z, then the Cayley graph is again circulant matrix. So, why is that true? Let us check. So, we take now any subset S of z modulo n z and we take it to be symmetric subset. So, now what we want to look at it? We want to look at it the A gamma of G comma S. So, note that so how this A gamma of G S is defined. The ijth entry is going to be, it is 1 if ij is an element of this edge set of gamma Gs, 0 otherwise. So, this is how the adjacency matrix is defined. Now, as far as the edges are concerned, so we already know that the I and j, so this edge, there is an edge between these two if and only if j minus I, this is you demand it to be element of S. So, that means this is given by the bracket j minus bracket I. So, if you think about it, so this can be captured by the indicator function of capital S. So, you take this delta S to be a indicator function from z modulo n z to 0 and 1, where delta S of x is exactly 1 if x is in S and 0 otherwise. If we look at this delta S, so this is an indicator function, then it is clear that A gamma Gs of ijth entry is exactly delta S of this j minus I. Okay. So, in particularly we have obtained this Cayley adjacency matrix of the Cayley graph in terms of this circulant matrix associated with this indicator function of S. So, that means the matrix that we got is indeed circulant matrix. So, this is indeed circulant matrix. Okay, now the question is what are all the eigenvalues that we can have it for this circular matrix, and Fourier analysis actually gives us a very explicit description of the eigenvalues. So, before proceeding to that, like let us first make some important lemmas, okay, then that will help us to actually get the eigenvalues for this type of circular matrices. Okay, so let me state this lemma, which is an important piece of information, and this indeed connects the two products that we have on this CG. So, one is convolution, another one is the product. So, Fourier transform, we know that it takes the convolution to the pointwise product. So, we make use of that and then try to get some information about this operators. So, let us fix the notation, let G be finite abelian group. So, now what we do, we fix an element A in this CG. So, then we define this left product. So, we call it LA. So, define LA to be map from CG to CG. Since CG is an algebra, so I can actually take any element and then take product, left product. So, let us say B goes to A star B. So, this is the map, and since the product is bilinear, so since we fix the first coordinate, so this is indeed linear map from CG to CG. So, now this linear map, what we can say about this? So, this linear map has an eigenvalue, okay, A hat chi for all chi in G hat. So, what we want to prove, indeed this LA is diagonizable, okay. So, not only it is diagonizable, and this irreducible characters, okay, so is diagonizable, and any chi in G hat is an eigenvector of this LA with an eigenvalue A hat of chi, and this is true for all chi in G hat. So, we have already seen that the irreducible characters, they form a basis for CG. So, in particularly you have this orthonormal basis of eigenvectors for this LA with these eigenvalues A hat chi. So, in particularly if you list this G hat to be chi 1 etc. chi n. So, then with respect to this basis G hat, so the matrix of this LA will look like A hat of chi 1 etc. A hat of chi n. So, this is how the matrix of LA will look like. So, let us prove this. So, its linear is easy. So, now we want to actually check that chi is indeed an eigenvector. So, we directly compute what happens to this. So, the convolution and addition, so they are like there are distributive laws among them. So, we are going to use that, and then we are going to also use that Fourier transform actually takes convolution product to the pointwise product. So, let us fix some notation. Let us start with chi being an element of g hat. So, then observe that we also fix n to be the cardinality of g. So, observe that if we take a star chi hat, so this is going to be a hat times chi hat. So, this is what the Fourier transformation does. Now, we already calculated what is chi hat. Chi hat is nothing but n times delta chi. So, this comes from the orthogonality relations of irreducible characters. So, that means this is exactly equal to a hat times n delta chi. So, this is what we have. So, now let us compute what happens to the right hand side. A hat times n delta chi, if you apply it on theta, so then by definition it is going to be a of theta times n delta chi of theta, which is exactly equal to n sorry, this is a hat theta times n delta chi theta, but delta chi is that delta function at chi. So, whenever theta equal to chi, so this one is going to survive, it is going to give n. So, this is going to be n a hat theta, and otherwise you get 0. So, basically a hat n delta chi applied on theta is giving these values on the right side. So, now if we apply the inverse of the Fourier transform, so using the fact that chi hat is equal to n delta chi, so then you can see that what we have is, so let me just rewrite this. So, you have this a star chi hat, this is what we wanted to compute, and we just seen that this is exactly equal to a hat of chi times n times delta chi. Since what we have on the right hand side, so this function is equal to n times a hat chi times delta chi of theta. Okay. So, that means I can actually write this a star chi hat to be, this is a scalar a hat applied on chi times n times delta chi. So, now if we use Fourier inversion, so then what we get is a star chi is equal to, so a hat chi and n will come out. So, because they are indeed scalars. Now, note that chi hat is n times delta chi. So, if you use Fourier inversion, you get chi equal to, what do you get is n hat delta chi will become chi if you use the Fourier inversion. So, that means what you get on the right hand side, so you get this is exactly equal to a star chi equal to a hat chi chi. So, this is what we get. Okay. Okay, so this means this chi is indeed an eigenvector with the eigenvalue a hat chi. So, chi is an eigenvector with eigenvalue a hat chi. So, that implies that this operator that we have defined LA is diagonalizable, and what we promise that is also true. So, this chi, all of them are eigenvectors and with eigenvalue a hat chi. So, this completes the proof of this lemma. Now, let us use this lemma in order to actually find all possible spectral values of this adjacency matrix of the Cayley graph. So, here is the theorem. So, let us actually just work through the theorem that states that if you list G as G1 etc. Gn, so this is a abelian group, finite abelian group, and then you fix S to be symmetric subset, and look at this gamma of Gs, that is our Cayley graph, and we also fix chi 1 etc. chi n to be the irreducible characters, which is in the G hat. So, now look at capital A, which is just A of gamma of Gs, the adjacency matrix of the Cayley graph. So, now what we want to do, we want to compute the eigenvalues of this adjacency matrix. So, let us start computing it. So, note that this delta S is given by summation delta small s s in capital S. So, this is the indicator function of this delta S. So, now we already know that the adjacency matrix is actually indeed obtained from this indicator function. Okay. So, if we use that information, then you can see that so let us take this operator, let us call it capital L. So, which is operator from CG to CG, where L of x is defined to be delta capital S star x. So, let us take this operator. So, now this operator is just a left multiplication like what we have seen in this lemma. So, this lemma is true for any A in CG. So, we are going to use this lemma for this operator that left to multiply by delta S. So, now according to that lemma, so what we get that the values chi i's. Okay, so what we get that this chi I, they are eigenvectors for this operator L with eigenvalue given by that chi hat of delta S hat of chi I, delta S hat of chi I. Okay. So, now let us compute this delta S hat of chi I. So, this delta S hat of chi I by definition is n times delta S chi I, the inner product, which is again by definition summation delta S of x chi I of x bar, x comes from 0. Now, since delta S is the indicator function, so this is going to give us exactly summation chi I of S bar and S in S. Now, since S is symmetric, so we know that this is exactly equal to chi I of S, S in S. So, chi I of S inverse is exactly equal to chi I of S bar, and since S is symmetric, we get this. Since S is symmetric, we get this last equality. So, that tells us that this lambda I, they are real. So, this lambda I are real. So, now the observation that we made actually tells that these chi i's are the eigen vectors with lambda I eigenvalue, where lambda I is given by summation chi I s in capital S. Okay, so now what is the connection between the adjacency matrix of the Cayley graph and this L? So, if we take the standard basis of CG, which is given by the delta function. So, then look at the matrix of this operator L with respect to the standard basis. So, then what we get? So, let us look at it. Let us call this B as delta 1, maybe let delta G1 etcetera delta Gn. So, this is the standard basis of CG. So, now this L is given to be from CG to CG, which takes x2 delta S star x. Okay. Now, look at the basis of the matrix of F with respect to this basis. So, this is going to be exactly equal to the adjacency matrix of gamma Gs. Okay. So, that means the eigenvalues we already computed for this L. So, the operator is not going to change. Okay. The same operator has this chi I as eigenvectors with the eigenvalues this delta S hat chi I, which is we computed it to be lambda I, which is summation chi I of S in capital S. Okay. They are real and these are all the eigenvalues. So, since with respect to the another basis, we are getting capital A to be the matrix of that operator. So, that tells us that this capital A and this L with respect to this chi I, so they are conjugate, and that means they share same set of eigenvalues. Okay. So, how do we check this fact? So, if it is enough to check this, okay, let us actually look at it. So, if we are looking at this ijth entry of this matrix, let us say bracket LB, the ijth entry. So, this is going to be, you take this delta capital S star delta Gj, and then you write it in terms of actually delta Gi. So, you write it this as sum of delta Gi, then you look at the ith entry in this. Okay. This is summation the bracket LB and then Ij delta Gi, I range from 1 to n. This is how the coefficient ijth coefficient of the matrix LB is defined. Okay. Now, by definition you can see that this delta S star delta Gj, how it can be reinterpreted. So, if we write it delta S star delta Gj, so this is going to be exactly equal to summation delta S xy inverse delta Gj of y, where y comes from G, then this is going to be equal to. So, this is going to survive, this term will survive only if y equal to Gj. So, that is the time this is going to survive, and this is going to survive only if x y inverse is indeed element of capital S. Okay. So, then you can see that you will be running over summation. So, maybe if we write this as some small s, so then so this y is exactly g j. Okay, I am evaluating at x. So, we will evaluate maybe at gi. Okay, that will be doing better. Okay, let us do this again. So, write x equal to, okay, take x equal to gi and then look at this delta capital S star gj evaluate at gi, which is going to give us summation delta S gi y inverse delta gj y in g. So, like I said, y equal to gj, that is the only thing going to survive, and gi y inverse we demand it to be capital S. So, that means gi gj inverse should be in capital S. That is the only time this summation is going to survive, and that means, so this is exactly is going to be equal to 1 if gi gj inverse is in capital S, 0 otherwise. And if we go back to the definition of our adjacency matrix of the Cayley graph, you can see that. So, that also has exactly the same property, because a I j is going to be 1 if g I g j inverse is going to be in S and 0 otherwise. So, that means the operator that we have constructed x goes to delta S star x. So, that has with respect to the standard basis exactly the adjacency matrix of the Cayley graph. On the other hand, with respect to this irreducible representations or irreducible characters, so that is diagonizable with the eigenvalues this lambda I. So, since they are conjugate, the eigenvalues are same. So, that means we can say that the eigenvalues of this capital A, so they are given by this lambda I, which is summation chi I of S, S is varying over capital S. So, these are all the eigenvalues of this capital A, which is capital A gamma G S. And not only that, the corresponding eigenvectors, they are indeed form an orthonormal basis, and those eigenvectors, let me call it as V I. So, they are going to be given by the evaluation at evaluation of chi I. Basically, it is given by chi I. So, just to normalize, we can take it to be 1 divided by the square root of cardinality of g with this coordinate chi I of g 1 etc. chi I of g n. So, basically chi I is the eigenvector corresponding to lambda I, which can be identified with this tuple of vectors. So, since the inner product is slightly different, so we want to normalize so that it becomes an orthonormal basis. Okay. So, basically what we proved, so given G finite abelian group and symmetric subset S of G, the eigenvalues of this A gamma G S of the Cayley graph or the real numbers given very explicitly summation chi I of S, S comes from capital S, where chi I they are given by this group characters. And not only that, the corresponding orthonormal basis of eigenvectors, they are also given by these VI's. So, these VI's, that will be the corresponding orthonormal basis. So, where the VI's are defined as follows: lambda I corresponds to VI. Okay, so this actually gives very explicitly what are all the eigenvalues that can be possible. For example, one can immediately apply to the circulant matrix and then get explicitly, because we know that what will be G hat for Z modulo n Z explicitly. So, in particularly we are actually getting eigenvalues of this circulant matrix for free. Okay, so this actually completes the application that I wanted to talk about. So maybe in the next class I will start with representation 3 of symmetric groups. I will stop here. Thanks.